Zoomer, zoomer, zoomer. Back, back, back. That's my plan. We're going to finish chapter, what did I say? We're not on chapter 9, are we?
Yep.
Are we on chapter 9? Holy smoke. So we'll finish vector operations today, and after the exam, we'll review the entire time on Friday, and then we'll just kind of mess around for the rest of the time. Okay, so this day is the last day of finals. And the last time, the last hour, in which finals are given on the last day. So some people have said they have plans of moving out by then and getting home by then.
That sucks.
So my question to you is, do you want your final exam online or in person?
Online. I guess online. I would like it online.
So that you can move home and have dad help you with the homework?
It's my only final, and I don't really want to stay for all those extra.
That's what I thought. But don't you have like a girlfriend that you want to spend all that extra time with?
No.
Just trying to help, man, just trying to help. Would there be great complaints? But online doesn't mean loosey-goosey, anything goes, right? I'm gonna be watching you, and you're gonna be taking it the way you did the other ones. Might surprise you and just show up at your dorm room and look over your shoulder. Because I'm here, I live here. Yes? Anybody at home? Anybody here would be opposed to doing an online version of the final exam, but it meets at the same time on that same day? Any problems with that? Works better for online because I cheat like heck. Hey. Okay. So we'll do it online. All right, we'll do it online, but you gotta be honest. You gotta do it right. But the third exam is in class, because I hate grading junk online. This way I don't really grade your final anyway. I just don't. You guys, then some goofball asks me, can I see my final? Then I have to hurry up and grade it. Make it match the score that I put in the grade book. So I'm like changing answers, so make them wrong and everything. Okay. Sir.
Can we do a question from the homework?
Yep.
Find T sub 4 of x, the Taylor polynomial of degree 4 of the function f of x equals Arctangent of x at a equals 0.
Okay. So I said it'll do you good if you would memorize some of these Mclaren series. And arctangent is one that I just could never memorize. I can memorize e to the x, sine of x, cosine of x, and the one that is the geometric series. Those I got in my head. I think I had them since birth. A few days after birth, I was interested in soiling my diaper for the first few days. But then after that, I started getting organized, and I knew those. So I know that e to the x looks like 1 plus x over 1 factorial plus x squared over 2 factorial, and so on. I know that one. I know sine of x. Sine was an odd function, and so it looks like x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And I know the derivative of the sine is the cosine, so there's no memorizing here. I just start taking derivatives, and I get 1 minus x squared over 2 factorial, because the 3 that comes down cancels, plus 5x to the 4th, where the 5 and the 5 factorial cancels. And so I can remember the cosine Mclaren series. And then the other one was that any geometric series has this as its sum. that would be a geometric series whose first term is 1 and whose common multiplier is x. So in general, we had it like that. And that looked like a plus a times r plus a times r squared. So in terms of 1 and x, it looks like 1 plus 1 times x plus 1 times x squared plus 1 times x cubed, and so on. So that's a geometric series with common multiplier x. It's there that I start in trying to get the series for arctangent, because I can't remember it. Only got this much memory space in my head. All the rest is filled with junk that I never use anyway, like how many cups are in a pint. That used to be there, I had to delete that, just so some of this would fit. Okay, so what I'm going to do is build this Mclaren series using the fact that the integral of 1 over 1 plus x squared is the arctangent. If you have this one memorized, just whip it out, but I don't. So be patient with me. I'm going to generate the derivative of the arctangent by replacing each x with a negative x squared. So that's where I'm going to start. First, 1 over 1 plus x squared looks like, so I'm thinking of that as 1 minus a negative x squared. I'm going to go over there and replace each x with a negative x squared. So I'm going to have 1 plus negative x squared plus negative x squared squared plus negative x squared cubed. So if I do the arithmetic to that, that simplifies for me as 1 minus x squared plus x to the 4th minus x to the 6th, blah, blah, blah. And so to get the arctangent of x, I integrate that term by term. That's how I need to integrate that. Where am I going to put it? I guess I'm going to put it right down here. So the arctangent of x is the integral of 1 over 1 plus x squared dx. And when you do any indefinite integral, you get a constant of integration. I put it first, and now I'm going to integrate each of these. And so I get plus x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7. But this constant of integration corresponds to the value of the arctangent at x is equal to 0. Because it's a Mclaren series. Does anybody know the arctangent of 0?
0.
Smaller. It is 0. Arctangent of 0 is 0 because the tangent of the angle 0 gives you the number 0. So that constant is 0. We can just wipe it out. So there's the series for the arctangent of x. Now we're going to generate the series for the arctangent of 12x by replacing each x with 12x. And so I'm going to have 12x here. Then I'm going to have 12x all cubed divided by 3. And then I'm going to have plus 12x to the 5th divided by 5. And so on. But this is only asking for the 4th degree polynomial. This is going to be a 5th degree polynomial, so that's one term too many. So for this web work problem, the 4th degree polynomial for the arctangent of x will just be these two terms. You can think of it as 0 plus 12x. There's no x squared, so you can put a 0x squared. I'm not going to do it, it screws up my signs. So it'll be, where'd it go? 12x minus 12 x all cubed over 3 factorial, because the fourth degree is missing. So you only get those 2 points, or those 2 terms in T4. Okay, so T4 corresponds to a fourth degree polynomial, but the coefficient of the power of 4 is 0. Okay? What I've written up here is T5.
So from those 4 on the right side, can we derive any series that we need?
You probably should know the log of x. You can get the log of 1 minus x from here by integrating both sides and changing the sign, right, because of UDU substitution. And then you can shift it to a different center by substitution and so on.
Where did 3 factorial come from?
Where did 3 factorial come from where?
In the final answer? You have to derive
Oh.
over 3 factorial.
It shouldn't be, it should just be 3. I just got the talking and writing. Should just be a 3, sorry.
How did you find the constant's actual value?
When we're making Mclaren series, we need the value of the function at x is 0 to be f of 0. Similarly, if we're doing it centered somewhere else, then if this were, say, at x minus 2, then I would need to know what the arctangent of 2 was. Okay. And then if it's not a series that you know, then you just start taking derivatives. I could have built the same polynomial by taking derivatives of this. Right? If you happen to forget any of these, use the general formula for Mclaren or a Taylor series. F of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial, blah, 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 blah. Right? So know that general formula as well. So if I ask you to find the Taylor series for f of x is x to the negative 5/2 centered at x is 1. Well, that's not a formula. You just start taking derivatives of x to the negative 5/2, plug in 1 for each x, and then put it in the formula for your Taylor series. Right? What else you got for me? Okay, then tell me everything you know about the dot product between 2 vectors.
Multiplying components.
Say it again.
You're just multiplying the components.
And you're going to get a scalar or a vector? Get a scalar. Dot product between 2 vectors is a scalar. It can be used to find the cosine of the angle between the 2 vectors. It can be used to find that thing called the projection vector, one vector on top of another. It can be used to find the work acting on an object, moving it from point P to Q. And if there's more applications, we really don't care. So now we're going to look at the other vector operation. It's the cross product. Vector cross product. I'll do all those next time. Okay, so I'm going to define the cross product of 2 vectors. Let's say we've got a vector, I use the A in my notes. Let's call vector A a 3-dimensional vector whose 3 components are subscripted A's. So those are real numbers in there. So let vector A be that, and vector B be this. Then A cross B is a vector orthogonal to both A and B. So you read this operation as cross, A cross B, is a vector orthogonal to both A and B, and is given by this formula. It is the product of A2 with B3 minus A3 times B2 in the I direction, minus the product of A1 with B3 minus A3 with B1 in the J direction, plus, so I've done A1, 2, 3, 2, 3, 2, 1, 3, 3, 1, so I guess I'm at 1, 2. A1, B2 minus A2, B1 in the K direction. And you think, I'll never remember that, and I don't remember that. I'm going to show you how I remember that. I remember that by computing a 3 by 3 determinant where the I, J, and K direction components are given as the first row. The components of vector A are in the second row, and the components of vector B are in the third row. Now, there are many ways to compute a 3 by 3 determinant. Here's the definition of how to compute a 3 by 3 determinant. You add a sum of 2 by 2 determinants. My first 2 by 2 determinant, imagine the first column being missing and the first row being missing. And so take away the first row and first column, and you have this 2 by 2 determinant. And then it's going to be in the I direction. Then we alternate signs. Now imagine the first row and the second column is missing. So cover up that middle column and cover up the first row and write down that 2 by 2 determinant, which is A1, A3, B1, B3. That'll be the J direction. And then finally, the last 2 by 2 determinant is formed by covering up the first row and the third column. So if you cover up the third column there in the first row, you have the 2 by 2 determinant with A1, A2 here, B1, B2 there, and remember that it's in the K direction. You may have done 2 by 2 determinants in another life, right? You do a 2 by 2 determinant by taking the product of the numbers on the main diagonal and subtract the product of the numbers on the reverse diagonal. So the main diagonal here gives me A2 times B3. The reverse diagonal gives me A3 times B2, and you subtract. Main diagonal minus the reverse diagonal. All the way down. All you got to remember is you alternate sign. You do that if you had a 4 by 4 determinant. You knock off a row and a column each time and make a bunch of 3 by 3 determinants, and you go plus, minus, plus, minus, plus, minus, plus, minus, plus. You'll compute determinants when you take your linear algebra classes. You'll compute determinants in Cal 3 when you compute, oh God, what was it called? I forgot. Oh, when you change coordinates, you have to change coordinates by figuring out your dx, dy, dz in terms of rd, rd theta, and rho sine phi cosine theta, d rho d phi d theta. I forgot all of those. I haven't taught Calc 3 in a while. Okay, so it gives a vector, and it's a vector perpendicular to the two vectors. So if you have two vectors, take their cross product, there's that right-hand rule that I can never do, right? We got a vector by my index finger, and I'm crossing with a vector that's my middle finger. It yields a vector that is my thumb. And if I do it the other way, it goes down. So it tells you which way it points. I could never do that. It feels like flipping off my teacher.
Yeah.
Okay, let's calculate these with a particular example. Okay. So, problem number 1, find the cross product 2, -1, 3, crossed with 0, 7, -4. We're going to find that cross product, and then we're going to show that our cross product is indeed perpendicular to both those vectors there. Okay, so the order in which you place it is important. In a minute, I'm going to ask you to find the cross product the other way so that you can see what happens when you change the order in a cross product. Okay, so we start by setting up this 3 by 3 determinant. Then put the first vector as the middle row, put the second vector as the third row. Then we break this up into the series of 2 by 2 vectors and compute those so that there's no memorizing. Just cover up the first column, write the determinant. It has the remaining numbers in it, and that goes in the I direction. Subtract, cover up the middle row, write the remaining 2, 3, 0, -4. That goes in the J direction. Cover that up, add it, 2, -1, 0, 7, reading across. And that goes in the K direction. Okay, now we take the products of each of the diagonals. So I have -1 times -4 is a +4, minus the product in the other direction. 3 times 7 is 21. So that'll be I. 4 minus 21 is a -17I. And we got this minus sign. 2 times 4 is -8. Minus the reverse diagonal product has a product of 0. So that gives me -8 in the parentheses. That changes the sign now to +8J. Now the last one, main diagonal, 2 times 7 is 14. Minus the product on the reverse diagonal, 0 times -1 is 0. And so I get 14K. (17I plus 8J plus 14K). So how can I tell if that vector is orthogonal to the two vectors we started with? Guess and check how?
Cross product.
Dot product. Remember, the dot product gives you the cosine of the angle between two vectors, right? So remind you of the formula, recall that the cosine of theta is given by the scalar v dot w divided by the magnitude of v, magnitude of w. If the vectors meet at a right angle, then the angle is pi halves, and the cosine of pi halves is 0. So if the left side is 0, that means the numerator is 0. V and W are perpendicular if and only if their dot product is 0. Vector V is perpendicular to vector W if and only if V dot W is 0. So I'm going to take the dot product between my resultant vector there, the cross product vector, with the two vectors we started with. So I'm going to show that the vector with components -17, 8, and 14 is perpendicular to both 2, -1, 3, and 0, 7, -4 by computing the two dot products.
Is the dot product considered like that whole cosine quantity or just one being dotted to another?
Not sure you asked what I think you asked, so maybe ask it again.
Okay, so is the dot product, like you see that cosine theta equals and then all that, is
Uh-huh.
all of that called dot product?
This, if I solve for the numerator, then the dot product between two vectors is the cosine of the angle between the two vectors times the magnitude of the individual vectors.
Okay, so that's just the definition of the dot product rearranged.
Yes.
Okay.
But in general, the dot product is done this way. I'll do it for this example. So -17, 8, 14 dotted with 2, -1, 3 is formed by taking the components in the first slot and multiplying them together. I'll write this step out. -17 times 2 added to, now you do it with the middle components, 8 times -1 added to 14 times 3. All right, 2 times -17 is -34. 8 times -1 is -8. 14 times 3 is 42. -34 minus 8 is a -42. -42 plus 42 is 0. So that one checks. Now let's take our cross product vector. -17, 8, 14, and dot it with 0, 7, -4. And so we get -17 times 0 plus 8 times 7 plus 14 times -4. So 17 times 0 is 0, 7 times 8 is 56. 4 times 4 is 16, carry that, yep, there's another 56, and I'm subtracting, and so we get 0. Okay? All right, I want you to find the cross product in the other way. So for the next part, I want you to find 0, 7, -4 crossed with 2, -1, 3. Cross product is not commutative like the dot product is. And the dot product V dot W is the same as W dot V. Cross product's not the same. Let me let you play with that and see how.
So we've been going over this in physics a little bit, and every time I see like a video of somebody do it, or even our professor, he says that that's not actually how you get the determinant of a matrix, or the, yeah, I think it's-
He says that's not how you get the determinant of a matrix.
he said that's not actually how you calculate the determinant of a matrix.
That's one of the ways. I wonder what he's referring to.
I don't know, because I've seen it on videos too, like,
When you compute a determinant, you can pick a row to pivot around. I'm picking the first row. And so that's where this IJK comes from. But if you have a 3 by 3 determinant, you can pick any of the rows. And then those numbers would be out there with the 2 by 2 determinants. So that's, there are shortcuts for 3 by 3s, but in the definition of computing the determinant of an n by n, it's typically given in terms of determinants of n minus 1 by n minus 1, smaller ones. But in practice, that's typically not how we compute it, because it takes a lot of steps. But I'm going to, just because we're at the end of the semester and I'm not going to show you 5 different ways to compute a determinant. Maybe when we're in that last week, when we can mess around with the 2 extra days, I can show you quicker ways to do it. But I'll do them by cofactor expansion. That's what this is called. Cofactor expansions.
Whatever's gonna give me the right answer on the exam.
That's all I'm worried about.
I'll go with that one.
You guys got linear algebra, you'll see bigger ones done in this way as well. And then there are tricks at doing the bigger ones. Like if I did a 5 by 5 determinant, I write it in terms of 4 by 4 determinants. That could take a long time. So you could do row operations to get lots of zeros in places, so that some of the places you'd be multiplying by 0. Oh, but that's linear algebra. I don't get to teach that one either. Okay, did you get this one?
Yeah.
How similar is it to that one? Not at all?
A little bit.
It should be the same, but opposite in sign. Should be the same, but opposite in sign. A cross B should be the same as minus B cross A. So let's figure out where you went wrong. Let's put our 3 by 3 determinant up here.
I did -1 times -4, and I went, okay, that's positive, that's minus 1.
That'll do ya. Okay, so you put them in the order that you see them. The first one goes in the second row, the second one goes in the third row. And now I write the 3 by 3s, the 2 by 2s. So to get this one, I cover up the I column and get 7, -4, -1, 3. The next sign has to be minus, cover up that, and I get 0, -4, 2, 3. And that's the J component. Now back to plus. And I've got 0, 7, 2, -1. That's the K component. I'm going to scoot over for my folks at home. And there it is. Now multiply the diagonals. So I have 3 times 7 is 21 minus a -1 times a -4 is 4. So by gosh, I get 17i. Minus 0 times 3 is 0. -4 times 2 is -8, so minus a -8. That's the J component. That's +8 in here, this makes it a -8J. Plus 0 times -1 is 0, minus 2 times 7 is 14. So I get minus 14K. So that is exactly opposite in sign, which means it's the same vector, but opposite in sign. So write that down. A cross B is minus B cross A for all vectors A and B. So A cross B is minus B cross A. Now I want you to take that first vector and cross it with itself. So I want you to compute 2, -1, 3 crossed with 2, -1, 3. So that you can see what happens to a determinant when any two rows are identical. Two, -1, 3, and cross it with itself. Zero the number or zero the vector? Zero vector, right? It's the vector whose components are all zero. A cross A is always the zero vector. I write out my little cofactors here. I have two across first column. I have -1, 3, -1, 3 in the I direction, minus 2, 3, 2, 3, K direction, plus 2, -1, 2, -1 in the K direction. And what you'll see is the main diagonal is the same as the reverse diagonal. And since you're subtracting, those are all going to be 0. But make sure you write it as a vector. Any vector crossed with itself is always the 0 vector. Anytime you compute a determinant of any size and two rows are the same, or if two columns are the same, that happens. You get a 0 as the determinant. A cross A is always 0. Okay, so just for fun, let's find another one you can compute. Oh my head, that's pretty bad. Keep on my glasses. It'll happen to you. Okay. Find minus I plus 2J plus 4K crossed with 5I minus J. Let's see if we can get 11 people get the same vector. What are you going to do for the K component for that second vector? Put a 0. Don't leave it just hanging. Put a 0 in there. Maybe if you took any kind of pre-calculus in high school, you did determinants. You learned something called Kramer's rule to help you solve systems of equations. No?
all those sounds familiar.
It's in there. That's one of the brain cells you had to partially delete. All right, I'm gonna catch up with you. Make sure you don't forget the minus sign between the first and the second determinant. Life is good. Okay, there's the cofactor determinants. All right, so 2 times 0 is 0. -1 times 4 is a -4. So I'm getting 4i. 0 minus 20 gives me -20 in here, but the minus out front gives me 20j. And 1 minus 10 gives me -9k. And then always make a quick check. You can always catch small mistakes by taking the dot product with one of your original vectors to make sure you get 0. So make a quick check. This gives me -4 plus 40. -4 plus 40 is 36. Minus 36 is 0. So that's how I know I'm good. Make sure your dot product gives you 0. If not, you blew a sign somewhere, or you multiplied a -1 with a -4 and got 41. Some goofy thing that you guys always invent on test time. Okay, now let me tell you some things about cross products. There's 2 important things about cross products. There's a version of the distributive property, right? So let me just write them all here and put them all together. So any vector crossed with itself gives you the 0 vector. Change the order in which you do the cross product, you get the same vector but in the opposite direction. V cross W is minus W cross V. The next one looks like some version of a distributive property. If I take 2 vectors and add them together, and then cross them with another vector, you can do that by adding the vectors first and then doing the cross product. Or if you're so fond of cross products, you can do the cross product with the individual vectors and then add them. So there's some version that looks like a distributive property. The cross product distributes through a sum. We had a law of cosines that found the cosine of an angle between 2 vectors using a dot product. If you're very fond of cross products, we have a law of sines. The law of sines looks like this, that the magnitude of any cross product is equivalent to the product of the magnitudes of a vector times the sine of the angle between the 2 vectors. So if you wanted to find the angle between 2 vectors using a cross product, You just take the cross product, then the magnitude, and then divide by the magnitude of the individual vectors, and that'll give you the sine of the angle between the two vectors. Take the inverse sine, and that gives you the angle between the two vectors. So it's the same angle that we were talking about, but this is the law of sines. One application of a cross product is that the cross product between two vectors has a magnitude that's equivalent to, right, this is vector V, and that's vector W. Vector V cross W, then the magnitude gives you the area of that parallelogram. The magnitude of V cross W is the area of the parallelogram with sides V and W. Sides that have those links. If I just take the magnitude off, then it looks like that picture. Now, in general, the area of a parallelogram is base times height, where the height is a segment that's perpendicular to one of the sides. So if we're thinking in 2 dimensions, then the height might be something, usually we draw it from here, right? But that tells you that if I multiply this by a half, I get the area of a triangle who has adjacent sides V and W. So 1/2 the magnitude of V cross W is the area of a triangle. With sides V and W. Now in 3 dimensions, if I have a parallelogram in one plane and a matching parallelogram in an opposite plane, and I connect those with sides, I have something called a parallelepiped. An example of a parallelepiped is a box. Now if you sit on that box, it gets squished a little bit. That's a parallelepiped. The volume of a parallelepiped, where sides of the base are V and W, and the other side is another vector, is something called the triple product. It looks like this. That if I have U cross V is a vector, then if I dot that with another vector, I get a scalar. Then if I take the absolute value of that, I get a positive number. And that positive number can be interpreted as the volume of the parallelepiped with U and V and W as 3 vectors forming its edges.
It's spelled parallel.
Yeah, I'm going to try. Parallelepiped. Whew! I think that might be it. Maybe it's an E. Maybe that's an E. Parallelepiped. Parallelo. E. Parallele. Parallele. Oh, I lost a bunch of L's. Parallelепипед. Probably a bonus question. How do you spell parallelepiped?
Please don't.
Well, yeah, then you could just look at the problem and say, I guess I spell it like that.
Oh, right.
That's an Aggie final exam.
Hartford, spell the volume of this equation.
There you go. And quickly, here's what you're going to use a cross product for in Cal 3. Remember I said in Cal 3, to write the equation of a plane, you need to know something about its direction. Well, you use the vector that's normal to the plane as the direction vector. You find two vectors that lie in the plane, take their cross product, there's that normal vector, then you put them into the equation of a plane, which you'll be told in your first week of Calc 3. Good? All right, practice doing these things, and we'll do some more examples. But I'm going to put a review sheet on Blackboard. I already have. It's already up there for those of you who worked through it a couple times. And we'll talk about that in class on Friday and test on Monday. Sound good? Sure. Sure. Happiness. Happiness to everyone.
Close enough.
Oh, I also meant to tell you guys, somebody asked me about what these write-ups look like with your WebWorks. I want all of them done. But in your WebWorks, I take your, I think we've had 14 WebWorks. So I take your top 12. Those are scores out of 100. So there's 1,200 points there. Then I take all your write-ups. I add them together. Make that a score out of 100. So I take those 1,200 points, take that 100 points. Now I got 1,300 points. Add them up, divide by 13, and that's your homework grade. So if you've not been doing web work and only been doing the write-ups, time to do the web work. If you need some open again, tell me.
I might need them all open then.
Example only over section 8, right?
Chapter 8 is the exam, yes.
So this is my.
Thank you very much.
Thank you. Have a good day.
Thanks.
What all goes into a math major, or like, do you know?
The math major?
On top of like the Cal 1, 2, 3. linear
Engineers take
algebra.
Cal 1, 2, 3, linear algebra, and probably a stats and differential equations. Math major is 13 classes. So we have a class called Intro to Proof. If you're a computer science major, that would be your discrete math class. Advanced calculus. Then you pick two courses that are called depth, which are the second semester of something. Usually the second semester of advanced calculus, second semester of differential equations, or second semester of stats. So you do a second semester, 2 of those, and then 3 of anything else, of upper level math. So math is really divided into applied math, pure math, and statistics. So by then you kind of know what you like, and you start picking and choosing just upper level math classes that you want to see what that kind of math does.
So it's a lot more than,
It's 7 more math classes.
because we don't have to take linear algebra,
Right.
or
But if you do take linear algebra, you have a minor.
yes.
Or if you take 2
GPQ.
semesters of your differential equations, your differential equations 3350 has linear algebra in it, but not to great depth.
Okay. I was just wondering like how much more it would be. That's a lot. 7 more
If you're
classes.
computer science, it's not, because there's a lot of overlap between computer science math and the math we have, so there are a lot of classes count twice.
Oh, okay. Well, I'm not. I'm
Yeah.
Mechie, so-
Mechanical.
Yes.
So if you just did the differential equations, I think you'll have a happy, healthy life.
Or linear, right?
But like I said, your linear, if you plan on going to graduate school, I would vote for differential equations 1 and 2.
Oh, okay. That's good.
If you just want to get your engineering certificate, then do the linear and DiffEq1.
Okay.
But a lot of the more advanced engineering math is partial differential equations.
Okay. All right. That helps a lot. Thank you.